Go ahead and move on to section 5.3, solving recurrence relations by iteration. Now, this might seem a little bit silly after all that we've done with recurrence relations already, but if you can generate a list of values in your sequence, then you can usually find an explicit formula for them. And if you can't, what we're going to do in the next section is play around with what happens if there's no obvious explicit formula. So let's start by just going through a few things here. So we have A0 is 1. A1 is going to be the previous term, which is 1 plus 2, gives us 3. A2 is the previous term, which is 3 plus 2 again, which is 5, and so on and so forth. So A3, we keep adding 2 to these, it's going to be 7. A4 is 9. A5 is 11. So we get the idea. Again, we're just adding 2 for each piece here. Well, how do we generate these values? Well, if we go through the list, let's see, 1, 3, 5, 7, 9. Well, how can we go? We're constantly going plus 2 to each, but is there perhaps a multiplier that might work? What we notice with each of these is that we can write them as the sum of 2 times some integer plus 1. So 3 is 2 times 1 plus 1. 5 is 2 times 2 plus 1. 7 is 2 times 3 plus 1. And you'll notice if we were to keep going here, then we would have a sub k is equal to 2 times k plus 1. So can we show that this explicit formula, or we should use ends here, that this explicit formula will work for this whole sequence? You can repeat the process of what we did before to go ahead and prove this using mathematical induction. Let's continue. A sequence is called arithmetic if essentially you're adding a constant term to get from one term to the next. Now, on the other hand, if you're multiplying by some constant, then that is called geometric. Now, let's see, we've seen plenty of examples at this point of arithmetic, including the previous one. Geometric is a little fancier, so if we wanted something here, we'll say that, I don't know, just for arithmetic, a sub k equals 2k plus 7. You could say b sub r equals, I don't know, negative 3r plus 4. Anything that's plus or minus a constant term will work for that. Now let's see here. Geometric if you have a constant multiplier. So geometric sequences are a little bit more exciting. We have some formulas that we can use to take the sum of geometric series, whether it's finite or infinite. One example, consider, let's say, sequence 2, or how about this? 1, 1/2, 1/4, 1/8, 1/16, so on and so forth. So you'll notice we have powers of 2's here, and this is technically 1 over 2 to the 0, 1 over 2 to the first. You could have instead, let's say, 1, 3, 9, 27, so on and so forth. Now, depending on what you know, if you've taken the calc sequence, you know that something like this shoots off to infinity if you were to try and add that up. Now, if you want to find the sum of an infinite geometric series, we can use the following formula. So take the sum from some indexed value, let's call it I, equals 0 to infinity, of a constant a times our common ratio or constant ratio to the I. This is equal to your constant times 1 over 1 minus r. Now, there do have to be boundaries on this, because if you leave r unbounded, or, well, essentially, if you leave r unbounded, you can shoot this off to infinity. Of course, if you're adding up some exponential number, well, this is exponential. If the numbers are getting smaller, we can come to a sum. If the numbers are getting larger, it shoots to infinity. Now, consider the example, oh, we forgot to give bounds. So the absolute value of your common ratio must be less than 1. If it's equal to 1, well then, again, 1 plus itself infinitely many times shoots off to infinity. So in other words, absolute value, that's saying that -1 is less than r, which is less than +1. So let's consider for a moment this example. Say we have 2/3 plus say 2/9 plus 2/27, and so on and so forth. So what we're seeing here is that we have a common ratio of 3. So 3 times 3, 3 times 3 times 3, and that constant of 2. So let's factor this out. Now, the catch here, in order to use this formula, we have to start with something to the 0 power. So 2/3 is not something to the 0 power. So if we factor out 2/3, that leaves us with 1 plus 1/3 plus 1/9, and so on and so forth. So out here, this is our constant a. So a is equal to 2/3 in this case. We can simplify this a little bit further so it's easier to recognize. We have 2/3 times 1 is 1/3 to the 0 plus 1/3 to the first plus 1/3 to the second, so on and so forth. So you'll notice here that any value from here on out can be written as 1/3 to a power. Now, once you have that exact value in every set of parentheses, that is your common ratio. So what we've found here is that this is an infinite geometric sequence, or series rather, with a, our constant term, is 2/3, and r is equal to 1/3. So by plugging in to our formula, this is equal to 2/3 times 1/1 minus 1/3. 1 minus 1/3 is 2/3. So you have 1/2/3 is 3/2. So it's 2/3 times 3/2, which gives us, in this case, just 1. You won't always get something that's 1. You could get something which is fractional, but anything like that, as long as you're plugging in, again, that your r is in fact bounded. We just do have to be very careful there, because if it's unbounded, it can get very crazy very quickly.